The next little chunk of this is simple pendulums. I'm going to record two quick little videos just to kind of set this up. The bottom line is when we looked at springs in simple harmonic motion, in a way they were simple because we know that springs follows this thing called Hooke's law, and conveniently, Hooke's law looks exactly like the condition for simple harmonic motion. We had for Hooke's law that the restoring force was equal to the spring constant multiplied by S, which is identical, even the same letter, as what we've been using for simple harmonic motion condition. Now we're going to bump it up and we're going to look at another system. The system we're going to look at is the pendulum. If you've seen a pendulum in our very first lab, we looked at a pendulum wobbling back and forth. The pendulum is definitely going through harmonic motion. It's vibrating back and forth or not. But to determine if it's simple harmonic motion, we need to look at the forces. We need to draw a free body diagram. We need to break down the forces, figure out which way it's accelerating. And if we look at those forces, and after doing some math, some analyzing what the restoring force actually is, if we can show that the force, if we can show that the force is some stuff multiplied by S, where S is the distance from equilibrium, the stuff just has to be a constant. So some things that aren't changing as the pendulum swings back and forth. So the mass may be involved. The length of the string may be involved. 9.8 may be involved. I don't know what else could be involved, but things that aren't changing as the pendulum swings back and forth, those sorts of things could be in those brackets. And as long as we can look at the pendulum and say that the force is equal to a bunch of constants multiplied by S, then we can say that the pendulum fits the condition for simple harmonic motion. Its force, restoring force, is proportional to the S. It's the more complicated proportionality. The spring was easy. It was just the letter K was in front of the S. For the pendulum, there might be more than the letter K in front of the S. So if we can do that, if we can look at the forces and show that the force pulling the pendulum back to the middle is a bunch of constants multiplied by S, then we can say the pendulum is simple harmonic motion. And even more powerful, we can take all those constants we got and replace them for K in all those crazy equations we came up with, and we can use all those equations for the simple pendulum. So I'm going to stop this video now. Oh, one more thing. When we say simple pendulum, when I say simple pendulum, it just means that you've got a light string and then some sort of heavy mass at the end. The string doesn't contribute any mass to the system, so it wouldn't be like sometimes in an old-fashioned grandfather clock, there's a pendulum in it, but it doesn't have a string. It has like a rigid piece of wood or something. That wouldn't be a simple pendulum because that rigid piece of wood would kind of add to it. A simple pendulum is just a mass on the end of a string, and as far as we're concerned, the only mass we have to worry about is the mass that's on the end of the string. We don't actually have to worry about the string itself. So I'm going to pause this video. You guys check out this proof and see if we can show that a simple pendulum fits simple harmonic motion.